Welcome back to our DC Circuit Lab 5. In this lab, we are diving into the fascinating world of 555 timer IC applications. Specifically, we will be focusing on two key configurations, the monostable and the astable circuits. In this lab, we have constructed two circuits on the same breadboard, the monostable and astable circuits. Let's take a closer look at the components and configurations used in each circuit. For the monostable circuit, we utilized a 555 IC, a 1 mΩ resistor to control the charging time, a 1 kΩ resistor at the trigger, a push switch and a 1 microfarad capacitor. Additionally, we incorporated a 3mm LED, accompanied by a 460 ohm resistor to protect the LED from excessive current. Moving on to the astable circuit, we employed another 555 IC along with a 100 kΩ resistor and a 2 kΩ resistor to control the timing of the circuit. To maintain the desired frequency, we utilized a 2.2 microfarad capacitor. Similar to the monostable circuit, we integrated a 3mm LED into the astable circuit, safeguarding it with a 460 ohm resistor. Our first experiment involves the monostable circuit configuration, where we will not only generate pulses of specific duration but also incorporate LEDs to visualize the output. By connecting resistors and capacitors in a specific configuration, we can precisely control the timing of the pulse. This allows us to explore applications such as push-button timers, one-shot triggers, and more, all while observing the mesmerizing glow of the LEDs. Moving on to our second experiment, we will explore the astable circuit configuration while continuing to incorporate LEDs. Similar to the monostable circuit, we will use resistors and capacitors to control the timing, but this time we will generate a continuous output signal with a specific frequency. By adjusting the values of these components, we can precisely control the frequency and duty cycle of the output waveform. As we witness the LEDs flashing on and off, we can understand the practical applications of the astable circuit, such as oscillators, timers, and even flashing LED circuits. Now, to further explore the capabilities of our circuits, we have introduced an additional 2.2 microfarad capacitor. By adjusting the values of capacitors, we can manipulate the charging and discharge times in the circuits. As a result, we observe a noticeable change in the frequency of the LED. The LED now exhibits a much slower pulsating rhythm, showcasing the influence of capacitor values on the overall timing characteristics of the circuit. We can also modify the timing characteristics of our circuits by adjusting the resistance values. By varying the resistance, we can effectively control the charging and discharging rates in the circuits. This allows us to fine-tune the timing of our LED pulses, providing us with even more flexibility and control over the behavior of the circuits. For instance, with a 100 kΩ resistor, we achieved a frequency of 3.2 Hz, meaning the LED blinked on and off every 150 milliseconds. However, when we increased the resistor value to 200 kΩ, the frequency became noticeably slower, having to 1.6 Hz or a blinking time of 300 milliseconds. This demonstrates how adjusting the resistor values allows us to control the timing and frequency of the LED pulses. Moreover, we have the flexibility to customize the on and off durations of the LED, enabling us to create unique and dynamic lighting effects. Thank you for watching.